So let us talk of a generic sensor, and let us call with a small s the stimulus of the sensor and the response of the sensor, which is the electrical signal, which is the response. Let us call it with a large S. Then of course the large S is a function of the small s. This function is called the transfer function. Of the sensor. According to this definition, of course, it does not mean to be linear. It is a generic one value function. Of course, this is a simplification which is valid in static condition. We need a monotone function, of course, because it has to be invertible. In principle, we can have something, for example, like this. To each value of the stimulus, only a value of the electrical signal response. And once we know the electrical signal, we can identify just one single value of the stimulus. So, since large S is the quantity that we measure, we need to be able to invert this function. This is S equal to F of small s. So we need to know F to the minus 1. So that from the electrical signal we can extract the stimulus. Okay. In principle, we can have any stimulus and any electrical quantity a signal. For example, we can have a sensor which provides us a voltage in response to a temperature. And so in that case, the temperature will be the stimulus, the voltage will be the electrical signal. This green curve will be the transfer function, and of course, once we know the inverse of the transfer function, we can obtain the temperature if we know the voltage provided by the sensor. Okay. This analytical expression is also useful in order to define the sensitivity of the sensor. This is a typical quantity which is indicated in every sensor data sheet. The sensitivity, which is defined as the derivative of the response to the stimulus. So it is basically the derivative of the function f as a function of s computed in a specific for a specific value of the stimulus. So for example, if this is S line, the sensitivity is going to be this slope, the slope of the tangent sensitivity. Okay. We also sometimes use the relative sensitivity. Which is the sensitivity divided by the response. So you see that the units of measure of the relative sensitivity are the inverse of the stimulus, of the units of the stimulus. Okay. These quantities are typically indicated. Of course, you should notice that these quantities can be defined only in association to a particular value of the stimulus. So when you have on a data sheet of a sensor the sensitivity or the relative sensitivity, it also has to be specified for which value of the stimulus the sensitivity is defined. Because of course this derivative depends on the position along the curve. Of course, both the two quantities are the larger the better. The larger the sensitivity, typically, not always, but typically, I don't want to be too quantitative here, but typically the larger the sensitivity, the better I am able to measure the stimulus, the quantity that I want to measure. Okay, of course we need to know this transfer function, and there are tolerances. The sensors are not all fabricated equally, because of course there are tolerances in the fabrication of the sensor, of the transducer, of the electronics. Therefore, if we take a production output of a certain set of sensors, the transfer functions will not be identical, and most important of all, will not be identical to the transfer function that we think we have. Okay. That is the so-called nominal transfer function. Okay, so the actual transfer function of a given sensor is different from the nominal transfer function. So by nominal transfer function, I think the transfer function that we think we have. Okay. And the reason for this difference typically is, let's say, fabrication tolerance. It's not the only reason, but it's the most important one. Fabrication tolerance is the reason for the difference. As I mentioned, fabrication tolerance of the transducer or of the interface. And so how do we solve this situation? Because if there is a difference, when we obtain the response, we make an error in associating the response to the actual value of the stimulus. So essentially there are two ways to resolve this difference, to obtain a convergence between the actual transfer function and the nominal transfer function. And the procedure by which we obtain this convergence is called calibration. By calibration, we mean the procedure which allows to reduce the differences between the actual transfer function and the nominal transfer function. Okay, it's better to stress the fact that we can only reduce the differences, because it's very unlikely to be able to perform a perfect calibration. So, just to draw an example in order to illustrate the point. if small s is the stimulus and large S is the response, we can have in blue here the nominal transfer function, but the actual transfer function of the sensor is this one in red. And of course the actual transfer function is different for each individual sensor. So what's the problem? Of course, if this is the stimulus, this is the response. But if we think that we have the blue transfer function, the nominal transfer function, when we have this response, we associate it with this stimulus. And so this difference is the error that we make in the interpretation of the measurement. Okay? So this is the reason why we have to reduce the difference between the two functions. Okay, how do we do that? There are two ways. One option is to make a coefficient calibration. Coefficient calibration. With the coefficient, what we do? Individually, for each sensor, we modify the nominal transfer function, we modify some coefficients of the nominal transfer function in order to let it be closer to the actual transfer function. Okay? So we modify the nominal transfer function to fit the actual transfer. Okay. Why I say we only modify the coefficients? Because typically we have a description of the nominal transfer function. For example, in the case that I have drawn here, I can assume that the transfer function is a parabola, and then I have, for example, two coefficients of the parabola. I assume that the parabola passes through the origin of the axis, so I have two free coefficients, and then I adjust these two coefficients in order to fit the actual transfer function, which means I adjust the parabola in order to have the nominal transfer parabola of the nominal transfer function be as close as possible with the actual transfer function. Of course, this must be done individually, typically with the sensor that is already accurate, that allows me to make some measurement and actually be able to measure what is the actual transfer function. Okay? Because we need to have some information of the actual transfer function to extract the coefficient that we need for the fit. Okay? So we adjust the nominal transfer function, and we have to do it individually for each sensor. And this is typically done commercially, okay? Because it's something that it is known, and for example, most of the sensors have in the electronics part some registers, some non-volatile registers, memories in terms of some registers in terms of non-volatile registers where we write the value of the coefficient. Okay, this is a very typical situation. The second possibility that we have is the so-called trimming. This is a calibration done by hardware. Okay. In trimming, what we do is we modify the sensor physically in order to fit the nominal transfer function. So we modify the actual transfer function by modifying physically the sensor in order to fit the actual transfer, the nominal transfer function. So the opposite of the coefficient calibration. Typically, the second procedure is much more expensive, since we really need to modify physically every individual sensor in order to adjust essentially the actual transfer function. Now, there are very many ways of doing this trimming, but for the moment we can consider it in very general terms. Okay. There are some additional qualities that are important for a sensor that I think we need to define, because they are typically used in a very qualitative way, while they have a very specific meaning. One, of course, is the accuracy of a sensor. So the accuracy of a sensor is the highest deviation from the true value of the stimulus. So for example, let's assume that this is the actual transfer function, the nominal transfer function, a line and this is something that we can have also if we have already done a calibration. So let's assume that after a calibration the actual transfer function is like this. Actually it's very close to the nominal transfer function, but is not identical. So, according to the definition, we need to take the highest deviation from the true value of the stimulus, and this means that if this is the nominal transfer function, this is the actual transfer function, I have to take the maximum distance on the abscissas, on the horizontal axis between the two functions. Let's assume it is this one. This is delta. Okay? So delta is the accuracy. Because this delta is the maximum error that I can make. If this is the true value, the real value, the true value is the real value of the stimulus, this is the response that I have, and since the red line is the nominal transfer function, the value of the stimulus that I measure is S star. So this delta is the maximum difference between the measured value S star and the true value, and therefore is the accuracy. Okay. Of course, since the calibration is never perfect, you still have a non-zero accuracy also after calibration. Of course, typically you have a much better accuracy, much smaller accuracy after calibration than before calibration, but still you have some. Also, the accuracy is a quantity that is always defined in the sensor data sheet. It is smaller. If a sensor has to be calibrated, actually, typically the accuracy is measured after calibration. Before calibration, it can be it can be really high. Sometimes in the data sheet the accuracy is given in absolute terms, sometimes is given in a percentage of the maximum value of the stimulus, the so-called span. This is the span. The span is the maximum range over which the stimulus can vary. In Italian we call it fondo scala. Span. In English sometimes it is given as a percentage of the measured quantity. One has to read carefully the data sheet. Okay? Other quantity is the hysteresis. In Italian is called hysteresi, with an accent on the first E. And the hysteresis takes into account the fact that sometimes the transfer function is different when the stimulus increases with respect to the situation in which the stimulus decreases. So, for example, if we increase the stimulus from 0 to the maximum value, we have this curve, and then when the stimulus go back to 0, we have a different curve. So we have a plot which depends on the orientation. It happens pretty often, and it really depends on the physical properties of the transducer. It's something that we do not want in principle, but we often have. Okay? And typically, so this is a curve with an hysteresis, and exactly by hysteresis we define the maximum difference between the two lines along the horizontal axis. So, for example, in this case, the hysteresis is going to be this part. when the difference between the two values of the stimulus when for the same value of the electric signal is maximum. Okay. So this is called H. H is the maximum error on the stimulus. So difference of S for the same large S electric signal. Okay, so I have to take it in the horizontal direction, considering the same large S. So this is going to be S down, and this is going to be S up. Continue with this small definition. It's a bit boring, but we need to have the same vocabulary. One other quantity is the non-linearity. That is also very common in sensor data sheet. This non-linearity is only relevant for linear transfer functions. Linear transfer functions are actually the most common transfer functions because they're easy to work with, and of course if the transfer function is linear, it's very easy to extract the stimulus when we have the response. But let's consider the situation of a linear nominal transfer function. So this is the nominal transfer function, and it is perfectly linear. For example, let's assume that the actual transfer function is something like this. Okay, this is the actual. So there are a few ways to define the non-linearity. The most common one is to consider the maximum error with respect to the nominal transfer function. So the maximum error with respect to the linear transfer function can be this one. Let us call it N1. Maximum error with respect to, when I write the WRT, this is pretty common, I mean with respect to the linear transfer function. There are different options actually to define the nonlinearity. This is the most common, but one has to be careful because sometimes the nonlinearity is defined in a different way, and so one must understand what is the case. Sometimes it is defined with respect to the best straight line, so to the straight line which fits the actual transfer function the best. So for example, in this case, this could be the nonlinearity. So it is the maximum error with respect to the best straight line. Best means best in terms of the least square minimum or some other principles. Or sometimes we have this is less common, let's say maximum deviation with respect to the internal calibration. This is the less common, but sometimes it is found. For example, what is done is the following thing. We consider this point, and then we compute the line which is tangent to the actual transfer function to this point, and then we extract the maximum distance between the nominal transfer function and this line in the span of the stimulus. So in this case it will be N3. It is important to understand these definitions, because if one wants to compare different sensors in terms of nonlinearity, for example, one has to be sure that the same quantity is intended in both cases, so that actually the two quantities can be properly compared. Okay. Few additional quantities. The precision, so the precision of a sensor is different from the accuracy of a sensor. I'm really stressing these definitions because let's say in normal language, accuracy and precision can be synonyms, okay? But in practice, in context of sensors, in the context of measurement in general, they are different quantities. Because with accuracy we intend, we mean the difference between the value that we measure and the true value. While on the other hand, precision is a quantity related to is a quality related to the repeatability of the results. So precision is related to repeatability. It is typically given in relative terms, delta R, and is the maximum error over the span. given in percentage terms. Okay, and the maximum error is the maximum error that I can do by performing repeated measurements in the same conditions for the same value of the stimulus. Okay. Maximum error that we make in the same condition for the same value of the stimulus. So, stimulus. So it is not important what is the true value of the quantity that we want to measure. If we always measure the same quantity, we have a very good precision, so this delta is going to be small. Even if the quantity we measure is always wrong. Okay? So this is the concept of precision. Why we make an error if we measure in the same conditions the same value of the stimulus? We can make an error because of many reasons, because of noise. We can make an error because of aging of the sensor, or we can make an error because of some, let's say, memory of the sensor, some as it is called, plasticity of the sensor, in the sense that, for example, if you repeat the measurement, the sensor remembers the previous situation and does not give you the same result every time. Okay? So the reasons here are noise, memory or plasticity, and aging of the sensor. So keep in mind that precision is different from accuracy, and also resolution is another quality. And is defined as the smallest increment of the stimulus that can be sensed, that can be reviewed. And it really can depend on a lot of things. Of course, if the resolution if we have a digital sensor, which means a sensor that provides a digital output, of course the resolution depends on the number of bits that express the signal, but of course can depend on a lot of other physical quantities. So the resolution is there for a quantity which is given in the units of the stimulus, and of course also in this case the smaller the better. Okay, so I think we are almost done. There is just one quantity, but I need to add another slide, that is the reliability. The reliability is a qualitative aspect and it expresses the capacity of the sensor to work without failure. Okay, it's a qualitative aspect, and of course, for obvious reasons, it can be only given in terms of a probability, because not all the sensors are created equal, so it is given in terms of probability. Which means in terms of statistical quantities. And the most common statistical quantities are the MTDF, which means median time before failure, and typically this is given at the max operating temperature. This is medium, no, not medium time before failure. Okay, it is given, it is so it is exactly the average time that passes from the start to the failure of the sensor, and of course it is obtained from a large statistics of sensors in this case. You need to consider that in practical cases this is the result of tests done at a temperature which is higher than the maximum temperature of operation. They are called accelerated stress test. In order to perform the test is in a reasonable amount of time. So one typically has to, in order to make the test, one has to operate the sensors at a higher temperature. And then typically there is a model which allows us to obtain from the test, from the time before failure at a high temperature, the time before failure at the reasonable operating temperature. Okay. In typical conditions, the time before failure go down exponentially when one increases the temperature. So, for example, one can perform an accelerated stress test in a day and then extract a medium time before failure at the maximum operating temperature of a few years. So this is something that is actually practical. And another quantity which indicates the reliability that is also obtained with stress test condition is the percentage of properly operating sensors after a given time at max temperature. So, for example, 90% of properly operating sensors after 1 year of operation at maximum temperature. The two things are correlated, so they are not given at the same time. According to some models, one can go from one type of indication to another type of indication of the reliability. But of course, you need to have a model of the reliability, which means a model of the distribution of the lifetime and a model of the effect of temperature on the lifetime. But also in this case, we have an accelerated stress test. Okay. Okay. Now after this we are going to look at the specific sensor, which is the accelerator. But first we stop for a few minutes.